Good evening, everyone.
Good evening, sir.
So, am I audible to you? I think.
Yes, sir.
Okay.
Good evening, sir.
Yeah, good evening, everyone. So just in 1 minute, we are starting. Okay, so today you have, good evening. Today you have your physics class, right? Your Friday and Saturday you have physics class, and Monday and Wednesday you have your chemistry class, right? So we'll carry on with physics, which we started with electricity, and we had a few doubts. Uh, in the last class we had done a revision of a chapter. We had revised one of the chapters. So is there anyone who is having any doubts with those revision topics? Shall we move ahead with electricity? Okay. I think we shall move ahead with electricity chapter.
Yes, sir.
So we were in electricity, we were trying to understand about electric potential. Okay, we were trying to get what is electric potential energy and what is electric potential. Okay. So does anyone remember what is electric potential energy? Yes, anyone able to recall about the electric potential energy? Yes, can anyone recall about the electric potential energy? Okay, just tell me what is gravitational potential energy? How do we define gravitational potential energy? Yes. Can anyone tell about the gravitational potential energy?
Sir, the energy of an object which is due to the height of the object, maybe.
Okay, so how is there an energy due to height? How can an object possess energy due to height? Yeah, certainly you are true because that's what we have learned. Okay, that's what we have learned up to now. So can anyone explain me that why will there be an energy on a height?
So we put in some effort to put the object on the top because gravity keeps pulling it down, maybe.
Yes, gravity keeps pulling it down and we are doing work. We are putting our effort. We are utilizing our energy to move that object up, to move that object up to a certain height. We are putting our efforts. We are putting our energy. So even if we apply by the conservation of energy, so by the conservation of energy, we can say that yes, there will be some energy stored in the object with due to some height. So if an object is at a certain height, it will possess some amount of energy, which we will be calling as the gravitational potential energy of the substance. Got it? So in the same way, so at every point, this thing is followed everywhere regarding the potential energy. See, first of all, let me justify you what is potential energy first. So potential energy of an object is the energy possessed by a body due to its position or configuration. Configuration means shape. Okay. So let's do a little bit about the potential energy. So potential energy, it is the energy stored in a body due to its height or due to its position due to its position or configuration. So energy stored in a body due to its position, shape or configuration is called potential energy. Okay. So just like we studied with the case of gravitation. Yeah. If you lift an object to a certain height, so we are doing some work. We are doing some work in changing its position, and hence our work done gets stored in the form of potential energy. And if we release that object from that position, so it will do some work as it possesses some energy. So if it's at a certain height, it possesses some amount of energy, and this energy possessed will be equal to the potential energy. So here the energy will be equal to the potential energy of the stone. Got it? In the same way, we can think of for the case of gravitational potential energy. For this is the gravitational potential. In the same way, we can think of electrostatic potential energy. So what happens in the case of electrostatic potential energy? In reality, we don't have anything something as height. Okay, that's it. If that's as per physics, we are not having height. We are just having the displacement. So here we consider, let's say we have a charge over here. So this is a positive charge. So suppose at this point we are having some positive charge plus Q. And now let us take another small charge and try to bring that charge. Okay, so now I am having a small charge Q located at infinite distance. When I say infinite distance, it means, so this is a charge, again, it's also positive in nature. So initially I assume it to be at infinite distance from this charge. Okay, so what will be the amount of work done over here? If I want to carry this charge from infinity to this point, hello. हम्म, ठीक है। हम्म, हम्म, Okay, so we can consider anywhere. So here I'm considering a charge of plus Q, and I think this color should be the best. Okay, so this is your positive charge, and I need to carry charge from this point to some point over here in the field. So everywhere, as I know this, I'm trying to move this charge from this point over here. So I need to apply some amount of effort, or I need to push it by applying some force. So therefore, when I want to move the charge from this point infinity, which is very far off, this is infinite, to a point A in which is in the range of this charge. So if I'm pushing it out, I'm doing some amount of work. I'm making some effort. So I have done some amount of work, which is denoted by W from infinity to A. So amount of work done from infinity to A. And since by the conservation of energy, so this work was to be equal to the amount of potential energy stored in that charge. Also here, we observe that it is a change of position. Since whenever you have the change of position, so we observe that this is a potential energy. So understood everyone that this is a potential energy, and this potential energy is given by the form is the amount of work done in moving the charge from infinity to a point in an electric field. Got it? And just like the gravitational potential energy, we can call this also as the potential energy, but this is our electrostatic potential energy. Everyone clear about the electrostatic potential energy?
Yes, sir. Sir, can you once repeat the definition so that I can note it?
Yeah, I'm writing it down for the electrostatic potential energy. You must note it down. What is electrostatic potential energy? It is the amount of work done in moving a charge of from infinity to a point. So if you are moving a charge from infinity to a point, so that work done will be equal to the electrostatic potential energy at that point. Got it? So it will be represented, or you can just write it like this. You can say that electrostatic potential energy, you can write that potential energy or electrostatic potential energy must be equal to the work done from infinity to a point. Understood this much?
Yes, sir.
Yes, sir.
Okay. Now we look for electrostatic potential energy, but now we're looking for just electrostatic potential. Now we don't want electrostatic potential energy. We are not talking of energy. We are just talking of electrostatic potential. Okay. So let's see what is electrostatic potential. Our next term here is electrostatic potential. And what things will be decided by this electrostatic potential? So electrostatic potential, it is the potential energy or we can say work done to a point in an electric field. So it is the amount of work done in moving a charge from infinity to a point in an electric field. The same definition is over here. Just a little bit of change. You can remove this electric potential to a point. So every the definition is changed. Another word is to be added over here. It is the amount of work done in moving a charge of, or you can say in moving a unit charge. We say it moving a unit charge. That's the only difference in the definition of both. See, electrostatic potential, it is the potential energy or work done in moving a unit charge from infinity to a point. So this we call as the electrostatic potential at a given point. For example, so in this case, we had seen that there is some amount of work done from this point infinity to A. Now, if I want electrostatic potential at A, so I'll write potential at A. The potential is represented by the symbol P. So potential at A would be equal to work done from infinity to A divided by charge, which is work done per unit charge. So this is what we mean, work done in moving a unit charge. So when we say unit charge, we have to divide it by Q. Okay, and this term will be called as electrostatic potential. So electrostatic potential is represented by V or volts. So SI unit of potential is volts. Whereas SI unit of electrostatic potential energy is joule, and it's just the same as gravitational potential energy. Got it? Any doubts over here?
No, sir.
Okay. Now let us see another term which is closely related to all these three, and that term is potential difference. So now this is a term which will be there throughout this chapter. Throughout this chapter, we will be talking of potential difference. So potential difference, again, it is a similar thing, but now we are not taking anything from infinity. We are not moving to infinity. We will just be dealing inside the field. So what is potential difference? We define it. It is the amount of work done in moving a unit charge from a point A to a point B in an electric field. So, what is potential difference? It is the amount of work done in moving a unit positive charge from a point A to a point B in an electric field. The similar thing, again, the definition would be of potential difference is it is just potential difference between the 2 points. So VAB, we write it VAB as the potential difference between the 2 points A and B, and it will be written as VB minus VA. So potential difference between the 2 points VAB will be given as VB minus VA. So potential at B minus the potential at A. Okay. So as we know that the potential at B will be given as work done from infinity to B, and potential at A is given at work done from infinity to B. Okay. So potential difference would just be VB minus VA, that is potential of A and potential of B minus potential of A. Got it? Now, in these terms, the terms which have been written, if I want to understand it like this, so I'll be talking this way. I have a charge over here plus Q, and so this is charge plus Q, and now I have another charge which is Q plus Q, which is a small charge. And I want to move this charge. I want to move this charge from a point A to a point B. Okay. So initially the charge plus Q is at point A. I want to move this charge to the point B. And let's say this is the charge. Here you have a charge as positive Q. This is the charge at this point. Now the potential difference between the 2 points will be, as per the definition, the potential difference has to be, it will be equal to the amount of work done in moving the charge from point A to the point B per unit charge. Got it? So work done by charge is equal to electric potential difference between the points A and B. Got it? So as a universal formula, you can remember that anywhere the electric potential difference will be equal to work done by charge, or you can also call it to be energy by charge. Understood it, everyone?
Yes, sir.
Yes, sir.
Okay. So let me give you a small question based on this, and let's try to do those questions. Okay. So do you remember the formula? The potential difference is going to be work done by charge. So a very small question over here we have. What will be the potential difference, or what will be the work done in moving a charge of, so you do what will be the work done in moving a charge of 2 coulomb through a potential difference of 6 volt. Yes, can anyone answer? Yeah, can anyone tell the answer?
12 Joule.
Yeah, the energy or the work done will be equal to 12 joule. Got it? Got it, everyone?
Yes.
Yes, sir.
Okay. Another similar question, hoping that most of you are a little bit aware about the mole concept. Okay. So here you have to tell what will be the charge of 1 mole of electrons. So how many of you are aware of 1 mole?
Sir,
there
actually,
anyone?
they deleted it for us last year.
Yes, sir.
Okay, I know it was deleted. So still I'm giving you knowingly that it was deleted, but still I'm asking if you know about the mole concept. That's good. Otherwise, I'll be just telling you the value of 1. Okay. So you just need to find the work done when 1 mole of electrons travel through a potential difference of, again, 1.5 volt. So do I need to tell you about mole also, or will you be able to do it? Yes, yeah, Siddharth, you are correct. 1 mole is equal to 6.022 times 10 to the power 23 particles. So I'm just writing you as a hint. You can take the help of this hint and start solving. You have 1 mole of electrons. So 1 mole of electrons is equal to 1.6 multiply 10 to the power minus 19, sorry, 6.022 multiply 10 to the power 23 electrons. So when I say 1 mole of electrons, I mean this many of electrons. Okay. So let us answer the first question. How we will answer the first question, which says you have to find the amount of charge. Yes. Can anyone find the amount of charge?
So this comes in like coulombs, right? 6.022 into 10 to the power 23.
These are electrons. These are the number of electrons.
So what's the unit for this? Still
Unit
be
for what?
1 mole of electrons.
1 mole of electrons means it's just like one dozen means 12. Okay. So if you have 1 mole of electrons, it means 6.022 multiplied 10 to the power 23 electrons.
Okay, sir.
Okay. Which formula to be used here? Which formula to be used here?
Sir, is it work done by potential difference?
There are two formulas that will be used over here. First, you have to find out the amount of charge, and the amount of charge will be given by the formula Q equals to NE. So the amount of charge Q is equal to NE, where Q stands for the total charge, N represents the number of electrons, and E represents the charge on one electron. The formula we did in previous class, I think the last week. How many of you remember this formula? We had done the formula Q equals to NE. Is there anyone who remember this formula Q equals to NE?
Yes, sir.
So Q is the total charge. Here we have Q is the total charge, N is the number of electrons, and E is the charge on one electron, right? So we want to find out the total charge first. See the first question here. The first question says what will be the charge of 1 mole of electrons? Also find the work done. First part is you have to find the charge of 1 mole of electrons. So we are also 6.022 multiply 10 to the power 23 electrons. So how many electrons are present? Yeah, how many electrons are present there?
6.022 into 10 to the power 23.
Okay. So we know here the number of electrons N is this much. 0.022 multiply 10 to the power 23. Okay. So this is the so if I multiply 6.02, okay. So 6.022 multiply 1.6 will give 9.6. So you have 9.6 multiply 10 to the power 4. Am I right? 9.6 multiply 10 to the power 4 coulomb of charges. They are moved when 1 mole of electrons are transferred. Okay. So this is the amount of charge, and now we will be using the work done. So can anyone find the work done now? Which formula to be used to find out the amount of work done?
Sir, can you show the question once?
Okay, see, there is the question. Okay, so we want to find here the amount we are given. So using the formula V equals to W by Q. So work done will be equal to V multiplied by Q. If you utilize, will be able to find out the amount of charge. So V is 1.5 volt multiplied by Q, that is 9.6 multiplied 10 to the power 4. This is the amount of work done. So just multiply 1.5 with 9.6. So
1.4.
that is 14.4. Yeah, 14.4 multiplied 10 to the power 4, or you can write it 1.4 multiplied 10 to 1.44 multiplied 10 to the power 5 joule of energy. Is it clear to everyone? Okay.
Yes, sir.
Now, any doubts here? See, now we can do some of the questions. We know what are the relationship between the electric potential and work done. We are able to get all of them. Just a little bit now. So, what role does the electric potential play with the charges? What role does the electric potential play? See, whenever we have to move a charge from a region of low potential to a region of high potential, so work must be done. We must have to push it. When you have to move a charge from a region of potential to a high potential. So if I talk of here in the previous example, my point B is at a higher potential and point A is at a lower potential, right? So can anyone guess what is the benefit of this term potential? Okay, just tell me for the previous one. Suppose I brought the charge from A to B. Okay, I brought this charge from A to B. So what will happen once I release the charge at the point B? Yes, what will happen to the charge at B once I release the charge from point B to the point A? Okay, see, when you bring the charge at the point B, it will and release it from the point B. So it will travel on its own to the point A. It will not require any effort as at the point B, the potential is higher and at point A, the potential is low. So the charge, it will travel on its own from point B to the point A. Got it?
Yes, sir.
So the charge will travel on its own from point B to the point A. This is the similar to the gravitational one. When I carry the charge from this point to a height and if I release it, so it will travel from this point to the ground level on its own. It doesn't require any effort. So in the similar way here happens. If I carry the charge from A to B, so charge from B will automatically travel to the point A. Now this is what happens in our real life. So what happens in our real life? We must have uh, listened to the people who say that charges move from a region of high potential to a region of low potential. How many of you have heard about this? That charges move from a region of high potential to a region of low potential. Okay. So how can we say that the charges move from a region of high potential to a region of low potential? Okay, see. So same thing happens everywhere for the electrical connections. Okay, if you observe the electrical connections, in your electrical connections, you always have two circuits. You always have two sockets. One is termed as the positive one or the phase. The other one is the neutral one. Okay, charges always travel from higher potential to the lower potential. If you touch a live wire, suppose there is a wire which is at a high potential. Suppose this is a live wire. In our regular life, we call it as a live wire. So you have a live wire and charges are passing through it. So this wire is at a higher potential V. And you are here on the ground. So the potential of ground is zero. Potential of ground is zero, whereas the potential of wire is V. And if you touch this wire with your hand, so your body, now charges start traveling through your body. As a result, you get electrocuted. You get here electric shock. How many of you, is there anyone who has experienced an electric shock?
Sir, not an electric shock, but in once that mosquito racket, sir, by mistake I touched it.
Yes. So over there, it's the same thing. Got it. So you have a live wire, and the live wire is at a higher potential. The ground is at a potential zero. If you touch it, there will be a difference of potential, and charges would tend to travel through your body, and hence you will get an electric shock. The similar case happens with other people also. So that is why, to prevent this, the people who carry on electrical repairs, they use plastic slippers, or they use slippers or shoes which are made up of uh, those materials which are insulators. Got it? Okay, so bye all of you. We'll see again this tomorrow. If there is any doubt, see us. Just you can message in the chat group.
Thank you, sir. Bye,
Okay,
sir.
thank you,
Yes,
sir.
bye all of you.
Thank you, sir. Bye,
Bye.
sir.